Hello everyone, today in this video we'll be discussing the third module of OS super important questions, and in this video we'll be discussing all the repeated questions which were there in the previous year exam. And make sure you watch this video till the end, easily gets more than 80% marks. All the important questions are covered, and before starting please do like and subscribe, it helps me make more videos like this. And without wasting any more time, let's get started. The first question is define deadlock. Okay, what are the necessary conditions for a deadlock to occur? Explain the different methods to recover from deadlock. So three questions are there. First is define deadlock and the conditions under which a deadlock can occur. And third is how to recover from deadlock. Okay, so let's understand what is a deadlock. Sometimes a process requests resources. Okay, there is a process P, it requests some resources. Okay, like CPU or input output or something, data like that. The process will request any of these. Okay, and these whatever it has requested, that is held by some other process. Okay, whatever it has requested, that already some other process has used, is using it. Okay, and the first process never gets them. The process which requested it never gets them because already some other process is using it. Okay, and why is the other process not leaving those resources? That is because the other process also has requested some other resources which is already being used by another process, and like this, like a chain, it's going. Okay, so in that case no process gets what it requests. Okay, so this situation is called as a deadlock. So if we imagine a real life situation, there is a car 1 which wants to go in this way, but this way is blocked by car 2 which wants to go in this way, and this way is blocked by car 3 which wants to go in this way, and this way is blocked by car 4 which wants to go in this way, and this way is blocked by car 1, and the process repeats. So car 1 is waiting for this to move, and this is waiting for this to move, this is waiting for this to move, and so on. So no one will move in this situation, right? This is a illustration of deadlock, and this also happens in the operating system. Whenever a process requests for resources, that resources which is already held by some other process, and so on. Okay, that is called as a deadlock. Okay, now what are the conditions under which deadlock can happen? A deadlock can arise only when all the below conditions simultaneously hold in the system. So until and unless all these four conditions, okay, four conditions are there, all the four should be there. Okay, all the four should be there, then only deadlock will happen. Even if three are present, fourth out of four, deadlock will not happen. Okay, so let's understand what are the four conditions. The first is mutual exclusion. Only one process can use the resource at a time. Okay, very simple. Only one process can use the resource at a time. Okay, and if any other process requests, it should be delayed. Okay, it should get delayed. Okay, got my point. Very simple. At a time only one process can use the resource, and if any other process request, it should be delayed. Okay, second is hold and wait, a process. This means that the process which is a part of our deadlock, that process has to be terminated, so that some resources which it has allocated, that will be given to this process, and this resource will be given to this process, and deadlock will be over. So one process will be selected and that will be terminated. That's the first way. So in this method also there are two things that can be done. The termination can be done in two ways: about all the process. Okay, that is also one method. About one process at a time until the deadlock is eliminated. This is another method. Okay, second is resource preemption. Okay, first one was deadlock, right? See, to eliminate a deadlock using resource preemption, some resources are preempted and given to the other process until a deadlock cycle is broken. While doing the same, there are three things which are to be taken care of. First is selecting a victim. Okay, so we have many processes and its resources which it has held. Okay, many processes have held some resources. Which process I have to select to terminate and give its resources to some other one? Okay, which process resources I will give to the other process? Okay, that decision I have to make. Okay, and which process if I take, that will be the my minimal loss. Okay, so if I take some process one, and whatever the task it has performed, to re-perform those task again, how much it will cost me? And the other process, how much it will cost? The other process, how much it will cost? Which is the process which I take which will give me the least cost? That one I'll take. That's called as selecting a victim. Second is rollback. Rollback the victim process to the previous state. Once processes resources is selected and given to the other process, at that time this process should be sent back to the previous state, so that it resumes its execution from the safe state again. Okay, rather than being in a incomplete state. Okay, third is starvation. Starvation means the same process I should not select again and again. uh, doing so, what will happen, it will that process will never get executed. Okay, that situation is called as starvation, that we have to avoid. Okay, so these are some of the techniques using which we can recover from deadlock. Okay, moving on to the second question, which is what is a critical section problem. Okay, and explain the requirements and Peterson's solution to the problem. Three questions are asked. What is critical section problem? Okay, so what is critical section? Critical section is a place where all the processes change variables, update data and tables. Okay, so it is a place in the code where all the updation of the data and the changing of the variable data, all those things happen. Okay, that portion is called as critical section. And when one process is using its critical section, no other process should be allowed to access the critical section. Okay, the second point. So the general structure of the typical process is shown in the below image. Okay, see here, this is the do while loop. The code is starting from here. Here will be having the entry section. The process will be entering from here. Only one process is allowed at a time, and the critical section will be here. Whatever changes it has to do, it will do it here, and it will exit from here. Okay, after that, the remaining section of the code will be executed. Okay, so this is the code snippet for the critical section. Okay, now the solution to the critical section problem must satisfy three requirements. So what is the problem here? Problem is we should not allow more than one process to execute the critical section at the same time. That is the problem. So how do we solve it? There are three requirements, which is which if satisfied, that will be called as a solution to the problem. Okay, so see here, the first one is mutual exclusion. If process pi is executing in the critical section, no other process should be allowed. Okay, first rule, if one process is executing, don't allow any other process. Second is progress. If no process is executing in the critical section, then only those processes which are not executing in the remainder section can be entering in the critical section. So the process, if nothing is present here, okay, here zero process are executing, so any one process from the remaining section should come and execute it here. Okay, at no point of time the process should be empty here. Okay, every time something should be executing here to maximize the efficiency. Okay, second thing is progress should happen. Third is bounded waiting. If there exists a bound or a limit on the number of times the other process are allowed to enter the critical section, so there should be a limit how many times one process can enter to the critical section before any other process has entered. Like for example, p1 entered critical section. Okay, and it got over, it came out again, p1 can't go. Okay, some other process has to go execute and then only p1 can go. Okay, like that. So how many times consecutively one same process can go back to back until that limit should be there. Okay, there should be a limit defined such that one process can go n number of times only until any other process will go next, and then only the previous process will go. Okay, that limit will be also applicable here. That is called as bounded waiting. Okay, so now what is a Peterson solution? In Peterson solution, it's restricted to two process pi and pj. Okay, Peterson solution is defined for two process. Okay, two process. Now it requires each process share two data items. So process pi and pj both will have these data items. What is the data items? Int turn is a variable of type integer, flag is a variable array of type boolean. What does these two things do? Turn indicates whose turn it is to enter the critical section. If turn's value is I, okay, if turn's value is I, pi will enter. If turn's value is j, pj will enter. And flag I indicates if process pi is ready to enter the critical section or not. Flag I indicates process pi is ready or not. Flag j indicates pj is ready or not. So these two things are there in Peterson solution, in turn and boolean flag. Now the structure of the process pi in Peterson solution. Here the code starts from here. Do while loop is here also, and first flag of I will become true. Okay, flag of I means process pi will be entering the critical section, and next turn is j. Okay, next turn who will enter? J will enter. Now while flag of j is true and turn is equal to j, turn j we have set here. And if flag of j is equal to true means if flag of j means j is executing. Okay, flag j is true means j is executing, pj is executing. So if this is true and this is true, that means it will keep on going and the process will be continuing. Okay, j will be executing. And when this will be over? This will be over when flag of I will become false. If flag of I will become false, then we'll be going to the remainder section, and the previous process which was pj, that will be executing. Okay, so using this code, what's happening is one time pi will be executing and another time pj will be executing. Okay, these variables are just for the reference here. Okay, so it does not indicate that always it will be j, it will be changing to I as well. Okay, this will also be changed to I whenever it is I, that time whatever the process I is there, that will get executed. Okay, so this is the code snippet you need to write in exam. So about the Peterson solution, and after that you have to write the proving the solution. Okay, so as we had discussed, there are three requirements. Okay, three requirements are there. If these three requirements are satisfied, then only that solution is valid. Now let's see if Peterson's solution satisfies those three requirements or not. Okay, first is mutual exclusion, second is progress requirement, third is bounded waiting time requirement. Okay, let's understand if mutual exclusion is met or not. Okay, in the Peterson solution, for that what we have to do, at a time only one process is allowed. Okay, the requirement of this is at a time only one process is allowed. That is called as mutual exclusion, right? One process should be allowed. If pi is executing, pj should not be allowed, and vice versa. In case flag of I and flag of j both are true, means both are eligible, pi also wants to go, pj also wants to go, at that time turn decides which one will be executed, because turn can either have I or j, both it can't have, right? So which one, whatever turn will be having that value, that will be executing, that process will be executed. Okay, if turn has I, pi will be executed, if turn has j, pj will be executed. Okay, so here mutual exclusion is happening because of turn variable. Okay, next is progress and bounded waiting. How can we ensure that progress is happening every time, at no time the critical section is empty? Okay, how can we ensure that? A process pi can be prevented from entering the critical section only if it is stuck in a while loop. Okay, how can process pi will not execute if the, see, suppose that critical section is empty. Okay, this is critical section, it is empty. Now if process pi wants to enter here but it's not able to enter, when will that happen? It will happen if it's stuck in a while loop, but it will never be stuck in a while loop. Why? Because flag of j is equal to true and turn of j is equal to turn is equal to j. If both these conditions are true, then only it will be stuck in a while loop, but both of these conditions can't be true. Why? Because if flag of j is equal to true, turn will be I, right? We had said that flag of I is equal to true we had set, and turn is equal to j we had set, if you remember. First I'll just show you. See here, at the top we are not setting the same thing. Flag of I is true and turn is j. Okay, so never these two will be same. So this will never get stuck in a while loop. That is the insurance that progress will always happen. Okay, and if p of j is not ready, flag of j is false and pi enters. Okay, so pj will execute until it becomes not ready, and then flag of j becomes false and pi enters. Okay, if both are ready, then the process that can enter the critical section, turn decides. Okay, turn whatever it has, if I it has process I will execute, if j it has process j will execute. Okay, because of this pi will enter the critical section always, it will never get stuck. That is progress. And after at most one entry of pj, bounded waiting. Okay, after, and pi cannot enter again and again. Why? Because after once it has entered, the flag of that becomes false, right? Flag of I becomes false after once it has entered. See, if you see here in the code, after entering the critical section, flag of that particular value becomes false, so that it will not enter again. It will enter again only after j has executed and this has become true. Okay, so consecutively it cannot execute, means the same process cannot execute consecutively back to back. That ensures that there is bounded waiting. Okay, so these three conditions are satisfied and you have to write this in exam. Okay, moving on to the third question, very important, which is the banker's algorithm. Okay, so this has been repeated almost in all the papers, previous papers, in the previous schemes as well. So let's understand how do you solve any kind of this question if it comes in exam. Okay, so the what they will be giving is, they will be giving you a matrix here. Okay, you'll be having allocation, max, available, and process will be given, and the resources will be given, resource A, B, C, D, and the values are also some given here. Okay, so let's understand what we will need to do. First question is, what is the content of the need matrix? Okay, so we have to calculate the need matrix. Okay, what do you mean by need matrix? Let's understand this one by one. Need is equal to remaining need. Okay, what they mean by need is remaining need. Okay, that is max minus allocation. Okay, always remember remaining need will be max minus allocation. Now why do we do max minus allocation? Now see, what's happening here actually is, here is the some resources are there. Okay, A has some resources, like A is one resource of A is available, 5 resource of B is available, 2 resource of C is available, and 0 resource of D is available. These are the available values which we have. Okay, and among these available values, some are already allocated here to the process. Okay, 0012 is allocated for P naught, means 0A is allocated to P naught, 0B, 1C, and 2D. These are allocated to P naught, means P naught already has these values. Okay, P1 has 1A, 0B, 0C, and 0D. P2 has 1A, 3B, 5C, and 4D, and so on. So each process has some resources already with them. That is called as allocation. Now, to execute the process, it requires a maximum limit. Means, see, in the first case, 0A, 0B, 1C, and 2D. This is what P naught already has. And to execute this one, okay, I'm talking about execution. To execute this one, it requires some more resources. So it requires total of 0A, total of 0B, total of 1C, total of 2D. Okay, it requires these many resources to get executed. Does it already have this many resources? Yes. So it will execute easily. Done. Second, P1. P1 has 1000. But if it wants to execute, it needs 1750. Can it execute? Does it have all this already allocated? No, it does not have. So it cannot execute like that. Okay. So you understood what is max? Max means how many resources it requires totally so that it can execute. Okay, and what is available? Available means how many are available so that we can allocate it. Okay, like that, how many are available so that we can allocate it here, and after allocating it we can check if it's satisfying the max criteria or not. Okay, so when we do this question, you'll understand. So first that asked what is the content of need matrix. Okay, why we are calculating the need matrix? See, some resources it already has. Okay, the processes have some resources already allocated. Okay, and maximum need is this much. Now how much more it requires? How much more it requires means the difference between max and allocation. For example, see, process P1, okay, it has 0B. Okay, it has 0B, and it requires 7 max totally. So how much it requires? 7 minus 0, right? So if you take a different number, so suppose that P3 and C, it has P3 has 3C, and it requires 5C for execution. How much it requires more? It requires 5 minus 3, 2 C's it requires. So subtracting max minus allocation gives us how much remaining need is there for that process to get executed. Okay, remaining need max minus allocation. So like that only we do here. So what we do is this minus this minus this minus this minus this. Okay, these four values when we subtract we'll get 0 0 0 0, because already whatever is required it already has. That means the remaining need is 0. For this what will happen? Second one, P1, 1 and 1, it's already fulfilled. 0 and 7, so it will become 7. 0 and 5, it will become 5. 0 and 0, it will become 0. So 0750, right? 0750, like that we'll keep on subtracting max minus allocation for each of these, and we'll be getting these values. Okay, so this is called as the remaining need matrix. Okay, now our first part of the question is done. First part, it was to calculate the content of need matrix. Next, is the system in safe state? If this question you see, right, so Banker's algorithm is mainly regarding this question only. You have to check if it is in the safe state or not. That means deadlock will happen or not, we have to check that. So if yes, mention the safe sequence. Now we'll be calculating the safe sequence for this. Okay, for that you need to remember a few things. Okay, just make the same table here again in your answer sheet. Right, allocation here, the same allocation table, the max table which is given in the question, and also the available they had given in the question. Write this also, and the need matrix, remaining need matrix which you just calculated, this also you just copy paste it here. Okay, so we have this table ready with us. Now how do we use the Banker's algorithm now? Okay, so let's understand it step by step. Okay, see here. Okay, first is and here there is a safe sequence. The sequence means in which sequence if I execute the processes, means first which process, second which process, third which, in which sequence if I execute there will be no deadlock. Deadlock means if I try to execute this one but it's not able to execute because it does not have this much resources, it will go in a deadlock. Okay, how do you ensure that whenever I execute a process, it will be ensured that I have that many resources at that point of time. Okay, so let's just get started. You'll get to know what I'm trying to say. See here. Now, available I have 1520. Okay, first check for this one. What is the remaining need? Okay, always you have to check what is the remaining need. Remaining need is 0000. Whenever the remaining need becomes 0, that means this process can be executed. Okay, so first P naught will be executed. Okay, and we'll be eliminating P naught from the table, means we'll just not consider it. Okay, and one more thing, when one process is executed completely, at that time the resources which it has hold, that will be released. Okay, what do you mean by release? Release means 0a will be released, 0b will be released, 1c will be released, 2d will be released. Means it does not require these resources anymore because it has completed its execution, right? So when it releases these resources, it will get added up in the available. Okay, it will get added up into the available. So when one gets added here, this will become 3, and 2 gets added here, it will become 2. So it will become 3 and 2. Okay, so currently I have 1, 5, 3 and 2. This is my available resources with me. Okay, next I'll check in the sequence. I have P1. Okay, now P1, what is the remaining need? The remaining need is 0750. It requires 0a and 7b and 5c and 0d. Do I have that many resources available with me? I have 1a, which is more than this. Okay, fine. I have 5b, but it requires 7b. Okay, so I cannot satisfy its need. I have to satisfy all of this, then only then only I will be able to consider that. Okay, even if one of them does not satisfy, like in this case 5 and 7, it requires 7 but I have 5 only, so it does not satisfy. We'll skip it. We'll skip and move to the next one, P2. Now P2, you check 1002, it requires 1a more and 2d more. Okay, do I have 1a? Yes, I have. Do I have 2d? Yes, I have. And 00, it can be ignored. Okay, so 1 and 2 can be given to this and this will be executed. Done. So I'll be considering this one. Okay, P2 I will be executing. Okay, whenever in a sequence I get one resource, I'll be executing that. Means the process which can be executed, I'll be executing that. And once execution happens, it will release all the resources which it has held, right? So it releases this one. 1 is released from here, so this will become 1 plus 1, 2. 3 is released from here, so it will become 5 plus 3, 8. 5 is released from here, this will also become 8. 4 is released from here, it will become 4 plus 2, 6. Now I have this many available resources. Next, I'll move on to the next sequence. P3. P3, what is the requirement? 0020. Do I have that many resources so that I can give it to this and it can complete its execution? Yes, I have 8, but it requires only 2. I can give it, rest all are 0. So once I give it, it completes its execution and releases the resources. So P3 is executed. Okay, after P2, P3 will come and it releases the resources. So I'll add it up. 0 plus 2 is 2 only. 6 plus 8, it is 14. 3 plus 8, it is 11. 2 plus 6, it is 8. Done. I have this many resources now. Next, can I satisfy this with these resources? Yes, I can satisfy. So 14, here it is 6, 11, here it is 4, and 8, here it is 2. These are all less and I have more, so I can satisfy. So I'll give it to this and satisfy its requirement, and this will also be executed. P4 is also executed. After P4, it will release the resources. It has 1c here present, so this will become 12, and 4d it has, so this will also become 12, and this is 2 and 14 only. Okay, now after this I'll go back and check P1. Okay, after this I'll go back and check P1. So can I satisfy P1? 2, 14, 12, 12, 0, 7, 5, 0. Obviously I have more resources and its requirement is less now, so I can satisfy its need. So I'll satisfy P1 and P1 will also be executed, and hence if we go in this sequence, at all the times we'll have enough resources so that process will execute completely. Okay, so this is the safe sequence. Got my point? Okay, next question was this is all what you have to do. Okay, so next question they had asked, if a request from a process P1 arrives for 0420, can the request be granted immediately? Okay, we can just check this same table and get to know. See, process P1. P1 is here. For the P1, how many okay, for the P1, how many allocation is there? 1a it has, and 0b it has, 0c it has, 0d it has. Okay, and the requirement is coming for 0420. Okay, 0420, 0 this will be satisfied, but 4 this will not be satisfied, 2 this will not be satisfied, 0 this will be satisfied. So for b and c it will not be satisfied, but there is some availability here, right? So 4 from here, if I give 4, this will be satisfied, right? And 2 from here, the 2c if I give, that will also be satisfied. So based on this, I can tell that this request can be granted 0420, because the available ones I have, also some allocation is here. If we combine them, allocated resources of p1 and available resources which I have, this need can be satisfied immediately. So my answer will be yes, the process p1 request for 0420 can be satisfied immediately. Okay, can be granted. Okay, that was about the banker's algorithm. Very important question. All the previous papers have, so please don't miss that question. Okay, you just have to follow the same process. Okay. Moving on to the fourth super important question, which is what is resource allocation graph, RAG. Consider an example to explain how it is useful in describing a deadly embrace. Okay, means how it describes a deadlock. Okay, by using resource allocation graph, how can you identify if there is a deadlock or not? Okay, so basically, what is resource allocation graph? Deadlocks can be described in terms of directed graph called resource allocation graph. Okay, so how do we depict it? Okay, before that, a few key terms are there. The graph consists of a set of vertices v and a set of edges e. So what it has, every graph will have a vertices and set of edges. The set of vertices can be partitioned into two different types of nodes. So the vertices can be of two types: partition vertices, process vertices and resources vertices. Okay, so p1, p2, p3 till pn. This is a set containing all the active processes, and r1, r2, r3 till rn consist of a set consisting of all resources types in the system. Okay, now pi arrow rj, what does this indicate? Okay, if there is a indicated arrow, directed arrow from pi to rj, it denotes that pi has requested for rj. It is called as request edge. And if rj is directly pointing to pi, that means rj is allocated to pi. Okay, rj is allocated to pi. Okay, this is called as assignment edge. Okay, in this case pi is requesting for rj, in this case pi already has rj. Okay, now the resource allocation graph is depicted for a sample scenario. Here there is resources r1, r2, r3 and r4. Okay, four resources are there, and processes are p1, p2 and p3. Now these arrows indicate what? These arrows indicate that R2 is allocated to P1. So P1 has R2 and P1 is requesting for R1. Okay, and P2 R1 P2 has R1. Okay, P2 has R1 and um, P2 also has R2. Okay, P2 has R1 and R2 and P2 is requesting for R3, and P3 has R3 and P3 is not requesting. Okay, so this is how you understand this graph. Now, how do we understand if there is a deadlock or not? In this scenario, there is no cycle. Cycle means like this arrows. Okay, like this arrow, if it is there, that is called as a cycle. But here, this can seem like a cycle. This is going here, this is going here, this is going here. But this is not going here. Okay, but this is going here like this, reverse. Okay, if it comes like this, then it is a cycle and deadlock will, this is a deadlock. Okay, but that's not the case here because the arrow is reverse way, and here also this is going like this and like this, it stopped. There is a no complete cycle formed anywhere, so there is no deadlock in this scenario. Let me show you a situation where there is a cycle and a deadlock. Okay, so see here, this is a deadlock, right? This is a deadlock. Okay, so that's all what the resource allocation graph does. We can detect the deadlock, and this example you have to write in the exam. Okay, next is explain how reader writer problem can be solved using semaphore. Okay, so let me explain you what is reader writer problem. Just imagine there is a notice board here, and many students are coming and seeing that notice board. Okay, just keep in your imagination, and in this notice board there are some changes happening. Means someone is coming and writing something, and someone is some other person is coming and writing some other thing, and so on. And the previous thing which was written, someone is editing it, and so on. So what will happen? Always this content is getting changed. Always this content is getting changed, and whenever the reader comes and reads and goes, it will have a different information than who came later on, right? This is the reader writer problem. If they are reading and writing at the same time, one reader will have one version of information, another reader will have another version of information, so there will be a mismatch, right? So that is the reader writer problem. How can this be solved using semaphore? Semaphore, it's nothing but a lock. Okay, semaphore will have two values, 0 or 1. Okay, 0 means lock, 1 means unlock. Okay, so see, reader writer problem happens when writer is updating and reader is reading at the same time. Okay, to solve this, semaphore can be used to lock. A data set is shared among the set of concurrent process. Readers can only read the data and writers can both read and write the data. Now what's the solution? Solution is allow multiple readers to read. Okay, allow multiple readers to read. Many readers will read at the same time, but when the multiple readers are reading, writer should not be allowed to update. Okay, and when the writer is updating, no reader should be allowed to read. When the writer is making some changes, no one should be allowed to read it. After the changes are done, then only they can read. And when they are reading, no writer should be making the change. Okay, so it will separate writer and reader so that everyone will have same version of information. Okay, so semaphore bit allows for the reader and writer. Okay, what does semaphore bit do? It is for the writer and the reader that can be used to allow or block during their task. If writer is allowed to write or not, that will be decided by the semaphore bit. Reader is allowed to read or not, that is also decided by semaphore bit. And by doing this implementation, we can ensure that at one time only reading or only writing is happening. Okay, so code snippet for the implementation is given below for the both writer and reader. So for the writer, this is the code. Here we have while true, wait wrt. Wait wrt means no one will be allowed to read. Okay, write will be locked here and only writing will happen. Writing is performed. Signal wrt means the signal will be sent that writing is over, then everyone can read it. Okay, in the same way reading is also here. Wait mutex. Mutex means that is the log given for the reader. Okay, if we make the mutex as 1, at that time reading is happening, and if whenever reading is happening, there should be no writing. Okay, writing should stop, and once the reading is over, we'll be informing to the writer that it is over, and the wait mutex will happen. Okay, wait mutex means the reading part is over. Whenever the reading part is over, read count will become minus minus, it will become 0. If it becomes 0, signal wrt means the writing can happen. Okay, so the first part is about the reading. Okay, this is the reading part and this is the writing part. Signal wrt will write and wait wrt will not write. Okay, and finally we'll do the signal mutex. That means reading can be resumed again. Okay, after writing is done, reading can be resumed again. Okay, need not write it exactly like this. Okay, no one reads in the examiners don't read the answers as you have written. Okay, so just write something similar to it, and you'll be getting the marks which are allotted to this. Okay, unless our examiner um, reads it fully, but that doesn't happen in most cases. Okay, so you can write something related to it, but remember that you have to include wait, signal, and mutex and read count plus plus, and if condition is here, there is another if condition. Okay, don't spend more time by hiding this one. Okay, you got my point, right? So let's move on. The next one is what is a monitor. Okay, explain the dining philosopher's problem using monitor. Okay, monitor is an ADT means abstract data type. Okay, so see here, what is a monitor, and explain dining philosopher problem using monitor. So what do you mean by monitor? Monitoring is a abstract data type. You can just imagine it as a empty space. Monitor is what? Empty space. What it does, it manages the access to resources. Okay, it is like a manager now. So first you had in your imagination empty space. Now what does monitor do? It will manage the resources. Okay, and ensure that only one process can access a resource at a time. Okay, one process will access the process can access one resource. That is called a monitor. Okay, it also ensures that one process at a time is active within the monitor. Okay, and monitor only handles one resource at a time. Okay, so two operators can be invoked on condition variable wait and signal. Okay, wait means wait and signal means execute. Okay, so what is the solution to the dining philosopher's problem? Okay, listen very carefully. It might look complicated, but if you listen carefully, it is not complicated and easily you can remember this one. Okay, so very important question. Solution to the dining philosopher problem using monitor. Okay, this is not semaphore, it is monitor. Okay, now, the solution to dining philosopher problem can be implemented using monitor as follows. Okay, just have to write few functions. Okay, first define the variables. Okay, define number of philosophers 5, and this is a p thread mutex and p condition condition. Okay, mutex to protect shared resources. Okay, this is the monitor, and condition variable for each philosopher. Okay, two things, mutex and condition variable. Now state is also given here. State can be three types. If it is 0 means philosopher is thinking, 1 means the philosopher is hungry, and 2 means the philosopher is eating. Okay, so basically the dining philosopher's problem, what it is, see, suppose that there's a philosopher sitting here and there's a chopstick, another chopstick, another philosopher is sitting, and philosopher requires two chopsticks to eat. Okay, two chopsticks to eat, but here if it takes two chopsticks, this philosopher cannot eat. But if this two chopsticks is taken by this philosopher cannot eat, right? So there is a mismatch here, right? So at a time only one philosopher can eat and its neighbors cannot eat, right? So deciding which philosopher will eat which time, and which philosopher will think which time. Think means not eating. Okay, so that is uh, that we'll implement using the monitor. Okay, so first we have defined these variables. Second is the function to test if the philosopher can eat or not. Okay, so void test int philosopher, int left, int right. Okay, int left is the left part of the philosopher, left neighbor, and right part of the philosopher, right neighbor. Okay, check if the philosopher can eat or not. If state is equal to 1 and state of left is not equal to 2 and state of right is not equal to 2, means, see, 2 means what? 2 means eating. Not 2 means what? Not eating. This is also not eating. Means left neighbor and right neighbor both are not eating, and the philosopher is hungry. Whichever the philosopher is present here, it is one. Sorry, not hungry. Yeah, it is hungry. One is hungry, right? So the philosopher which is seated in the middle, the philosopher is hungry, and the left neighbor is not eating and the right neighbor is not eating. In that case, the philosopher has both the chopsticks present and can use both the chopsticks to eat the food. Okay, so in this case the philosopher can eat. Okay, if this condition becomes true, that means philosopher can eat. So the philosopher state will become true, it will start eating, we'll print it, and also in the conditional signal we will specify it which philosopher is eating. Okay, this is the code for philosopher can eat or not. Second is to pick the chopstick. Two functions are remaining, one is pick up, one is put down. Pick up means taking a chopstick, and to take a chopstick, first the philosopher should be hungry. Okay, and then we'll check if the philosopher can eat or not. Okay, and if it cannot eat, it has to wait until it can eat. Once it eats, done, then it can unlock means it can give its chopstick so that other neighbors can eat. Okay, so this is the code for picking up the chopstick for eating. Second is after eating, put down the chopstick. If it puts down the chopstick, that means it is allowing the other neighbors to eat. Okay, so first lock the mutex. Okay, lock the mutex means it is thinking in the thinking state, and after that left and right is taken. If it has put down the chopstick, then it is checking that if its left neighbor can eat and if its right neighbor can eat. Okay, so if one philosopher has two chopstick, if it has put down means this will be used for the left neighbor, this is used for the right neighbor. That test we are doing here, if left neighbor can eat and right neighbor can eat or not. Okay, so this is one version of the philosopher's dining solution problem. If you get any other code which is more easier than this to understand, you can by heart that as well and write in the exam. But any of the code will do, just that you have to include the functions where checking is done and pick up the chopstick is done and put down chopstick is done. Again, I repeat that you need not have the same syntaxes available, everything should be same here, just it should convey the clear point. Syntax is not that important. Okay, convey the clear point, write your explanation what you want to say, and you can expect the allocated marks for this question. Okay, so a single mutex ensures mutual exclusion. Okay, each philosopher has a condition variable to wait when they cannot eat. If they cannot eat, they have to wait. Okay, for that a condition variable is there, the con signal, which was there, con wait. Okay, and three things are defined here: pick up, put down, and test. Pick up is for tries to pick up the chopstick and start eating if possible. Put down means finished eating and allows the neighbors to eat. Test means it checks whether the philosopher can eat or not. Okay, this solution prevents deadlock and starvation by using a monitor to manage the access to the chopsticks. Okay, so that's all. Don't miss any of these questions, and please do like and subscribe. It helps me make more videos like this. And thank you so much for watching. I'll see you in the next one.